Okay, so chapter 1, I know you guys got the calendar yesterday, is 3 sections long. It is all about definitions, terminology, that sort of stuff that we're going to be talking about. So not a whole lot of calculations we're going to be doing, more just knowing what all these terms mean that we're going to be using throughout the semester. All right, so let's see what we're going to get into today. All right, first definition, and you can paraphrase this for sure, is just statistics. What is this class? So statistics is a science of collecting, organizing, presenting, analyzing, interpreting numerical data in an effort to make decisions, to draw conclusions. So we as statisticians will figure out what data we're going to use, how we're going to get that data, how much data we need, how then to display, calculate, and interpret that data. Okay. All right, so you don't have to write this down. This is just kind of a scenario we're going to talk through as we do the rest of the definitions today. All right, so we have a hiring discrimination case. An airline has just finished training 25 pilots, 15 are male, 10 are female, to become captains. Unfortunately, only 8 captain positions are available right now. Airline managers announced that they will use a lottery to determine which pilots will fill the available positions. The names of all 25 pilots will be written on identical slips of paper, placed in a hat, mixed thoroughly, and drawn out one at a time until all 8 captains have been identified. A day later, managers announced the results of the lottery. Of the 8 captains chosen, 5 are female and 3 are male. Some of the male pilots who weren't selected suspect that the lottery was not carried out fairly. Do these results provide convincing evidence that the lottery was unfair? Okay, so again, 15 males, 10 females to start. Out of that group of 25, 5 females and 3 males were selected from the lottery. All right, so what evidence, and right now this is purely opinion related, would you need to be convinced one way or the other that the lottery was either fair or unfair? What questions would you have? Yep.
If the names were mixed around.
Okay, so we want to know like how those names were put in the hat or the bowl. I would want to know, were those pieces of paper identically the same size? Were they folded the same way? Were they the same type of paper? Was it mixed to start? Was it mixed between draws? Okay, so how was the lottery carried out? What else? Could any math convince you that it was fair or unfair?
The fact that there's more pilots at the start.
Okay, so we talk about like odds and proportions and probabilities. You want to use like some of those fancy math words, right? The odds are that really more males should have been picked than females based on who started. Okay, so we'll come back to that. All right, well, we got to define a couple more terms. The next pair of terms, you're going to need to be able to distinguish the difference between, and these are going to show up a lot throughout the semester, a population versus a sample. A population is everybody, a collection of all possible outcomes, responses, measurements, or counts that are of interest. So a population could be every single student in Jackson High School, or every person in Jackson Township, or every person in this room. Okay, it could be really big, could be really small, but it has to include everybody. Then we have a sample. A sample is a subset of a population. Okay, so if you guys are my population, I could say the sample is all the females in this room or all the males in this room. Or if Jackson High School is my population, I could say that you guys are my sample because you're a subset of that. Or if Jackson Township is my population, I could say students at the high school then would be the sample. So the sample has to be smaller than the population, a subgroup of the population, whatever that is. Okay, so back to our pilot example now. In the pilot example, who's the population? Who's everybody? The 25 people that were trained is the population in that example. And who is the sample, the subgroup of that? It is? Good. The 8 names that were selected to be captains from the lottery. Make sense? Okay, so population is the 25, and then the sample is the 8 that were selected. Okay, then we talk about, okay, we want to eventually use math and numbers to describe populations and samples, and that's where we get parameters and statistics. So parameter goes with population, easy to remember, start with the same letter. Sample goes with statistic, easy to remember, start with the same letter. So a parameter is some number that is used to describe a population. And a statistic is a number that is used to describe a sample. 99.9% of the time, we are using statistics, not parameters, because it is difficult to get data information from a population. Often they are large, and so that would be time-consuming, expensive, maybe just difficult to find all of pieces of data. We don't want to make sure we're not missing anybody if we truly are looking at a population. So statistics are easier to calculate because it is easier to find a subgroup. It is more cost effective, time efficient, and maybe easier to just find those pieces of data that we're looking for. There's a couple examples here. An example of a parameter, it says there are exactly 100 senators in the 109th Congress, and 55% of them are Republicans. So the numerical piece of data here we have is a percentage, 55% are Republicans, and that 55% is a parameter because it describes the population, all of the Congress members, okay? Then statistic, down here, we again have a percentage. It says in 1936, Literary Digest pulled 2.3 million adults in the U.S. 57% said they would vote for Alf Landon for president. So we have a number, but this time it's not describing everyone. It's only describing the people that were polled, the 2.3 million. So 2.3 million adults here is a sample. What's the population? Doesn't tell us what the population is. You have to figure that out.
All of the adults in the U.S.
It would be all of the adults in the U.S. or all the voting adults in the U.S. or whatever you want to describe it as, but it's going to be a larger group than just those 2.3 million that were surveyed. Okay, so to the side there, it says 5 out of 8, or 62.5% of pilots that were chosen were female in our little example. Is that 62.5% or the 5 out of 8, that proportion, a parameter or a statistic? It is a statistic. Why?
Because it's a sample of what the overall was.
Right, because we said that 5 out of 8 was a sample. The 62.5% describes that sample, so it is a statistic. Make sense? Any questions so far? Great. Okay, another pair of definitions that we need to know are the 2 branches of statistics. Okay, so we have descriptive statistics and we have inferential statistics. Sometimes we use one, sometimes we use both. Descriptive statistics are kind of like our starting place. It is in organizing, summarizing, and displaying our data. So these are the graphics, the charts, the mathematical calculations that we can get strictly from the data alone. Then inferential statistics is almost like a level 2. We're going to take those graphics, charts, calculations, and we are going to draw a conclusion. We are going to infer about what those numbers and pictures mean for whatever we're analyzing. Okay? So descriptive statistics should have no opinion in it. The researcher really shouldn't be able to skew it one way or the other. Well, I guess they could a little bit. They could, change the way the chart looks a little bit to go one way or the other. But inferential is when we're actually summarizing that information. Okay, and that's where we're drawing those conclusions, and that's ultimately the goal when we're doing statistics, is to find a conclusion about something. All right, grab a bag, pass them around. Everybody needs one. Okay, you're gonna get a little bag in a second. We're gonna do an experiment with our pilot example. So in your bag, you either have red and black or red and green. I didn't have as many green beads as I thought I did. Make sure you have 10 of one color and 15 of another once you get your bag. Okay, so double check that first. You don't have to take them out. You can just count them in the clear part. That's fine. Okay, so just make sure you get 10 of one and 15 together. The 10 beads represent the original females that were trained. The 15 beads are going to represent the original males that were trained to be pilots. Okay. 14 red. Yeah. 9 green. 1 green in here. Oh, sorry about that before. I'm sorry. Okay, everybody got 10 and 15? Okay, so we're going to do our own pilot example here. So the lottery was done one time. We had a specific result, 5 out of 8. But ideally, if that is a reliable result, we should be able to reliable and replicate that same experiment and be able to get the same results. If something is replicated and the same results are shown over and over again, we can make a better conclusion in statisticians. That's what we're going to try to do. So we're going to replicate it 23 times. You guys can have your own little experiment there. So you're going to close your eyes, and you're going to draw 8. Okay, you are choosing who's going to be captain. Once you have your 8 drawn, I want you to count up how many females you chose. So that would be either the green or the black, depending on what color you have. Okay? So you're going to count up how many green or black you chose, and then as a class, we're going to make a dot plot with this data. So dot plots, if you don't remember these from like middle school, it's where you take a dot and you just like stack them on top of each other. Okay? So that's what that's going to look like. All right, so once you know how many females you have chosen, you can put your beads back in the bag, and then you can come up and add your dot to our dot plot. Go ahead.
green one?
It's okay, I have extra if you don't find it. I'm not that worried about it.
Got it.
Everybody got it up there? Okay, so it looks like we've got one person that picked 0, 4 that picked 2, 5 that picked 3, 1, 2, 3, 4, 5, 6, 7, 8 that picked 4, 3 that picked 5, 6, 1 that picked 6, and 1 that picked 7. All right, so what do we think? Does this change your mind at all? About maybe your original interpretation? Was the lottery fair? Those of you that picked 5, 6, and 7, do you think the lottery was fair? Did you do it fairly? Close your eyes. You know what? Okay. What about anybody else? Convinced? Not convinced? Is it possible to pick 5? Is it likely? Probably not. But is it possible? So can we truly draw the conclusion that it was an unfair lottery? No, not necessarily. We could maybe like as a union, as part of the pilot union, we could request that they replicate it or do it with technology or maybe pick a better method than literally drawing things out of the hat, but we can't necessarily say it was unfair based on our data that we've collected, okay? Interestingly enough, your picture has a nice little shape to it. Did they recognize what that shape is? You guys might have learned it in a previous class. What is it? It's a bell curve. You guys heard that word before? We're talking a lot about bell curves in this class later on. So. Okay. Last question then. Well, I'll ask 2 questions. What branch of statistics does that dot plot we made represent? Got a 50-50 shot, right? Descriptive or inferential? What do you think? Descriptive. It is a display of our data. What branch of statistics does our conclusion represent? Inferential. Correct. We're drawing conclusions with that data we collected. All right. Do we feel like statisticians? That's it for 1-1. I'm done. All right. So remember, we're not going to start Math Excel until the end of this week, but you guys can do the orientation if you want to. You guys have an assignment in Polaris 1-1. You have 3 attempts on it, and it's due before you come to class on Friday. I would say you should at least be able to get 1 attempt done before you leave class today, and then you can go back and correct anything if you need to. All right, the beads, if you want to zip them up and put them back in my purple bin up there, maybe one person from each group can do that. I'm going to do the cell phone motto. Number 19 is my winner. Nobody stay. All right, you can have your phones.
Solid screen.